Okay, so we're going to start chapter 3. Chapter 3 just has 2 sections in it, and this is on quadratic functions. Okay, so I have an example to start with. A baseball is popped straight up by a batter. The height of the ball above the ground is given by the function f of t is equal to negative 16t squared plus 47t plus 3, where t is the time in seconds after the ball leaves the bat and y is in feet. So that's how tall the ball is in the air. And one thing to note on here that they talk about here is that while the ball is in fact going straight up and straight down, the graph doesn't appear that way because we are measuring the height over time. So at 1 second, here's where the ball is, 2 seconds, and then 3 seconds. So at 3 seconds, the ball is hitting the ground again. Okay. And somewhere here between 1 and 2 seconds, this is the max height that the ball will reach. Okay. So this gives us what's called a parabola, and this is a quadratic function. So let's go ahead and define those terms. So a quadratic function, I'm giving you 2 forms here. We'll look at a third form in the next section. But the standard form is ax squared plus bx plus c. Okay, and it's typically represented with p of x for polynomial, since this is a polynomial. And then the factored form. So the factored form, we're going to look at some factoring in a little bit. You may remember that from high school, but it's written as some sort of constant a times x minus r, and then that quantity is times the quantity x minus s. Okay, so we'll be working with both of those forms. And then our graph here, as I said earlier, this is a parabola, is what we call this shape. And a couple of features on this parabola. So this particular one opens down, while this one opens up. So your parabola opens either up or down if you're doing y as a function of x. It can open sideways if we look at x as a function of y. But we're just going to do up and down with y as a function of x. This part here where your parabola turns around, so first it's increasing and then decreasing. This is the vertex. And on a parabola that opens down, your vertex is a max. And on a parabola that opens up, your vertex is a min. Okay, so the max, we've already looked at an example of that with the ball. So rockets, all kinds of things like that, you're getting that maximum height. Where you might be interested in the minimum is if you had a formula that gave how much cardboard is needed to make a box that holds a certain amount of volume. Well, you'd want to minimize that so you don't have to buy as much cardboard to make that box. Okay. Also minimizing costs of production, so things like that. So there are practical purposes to maxes and mins. And then where we're crossing this x-axis here, these are our horizontal intercepts, or our x-intercepts. And they're also known as the zeros. The zeros of your function, and we're going to take a look at those as well just a little bit. So let's see if we have a good understanding of when things are quadratic. So y is equal to 5x squared minus 17x plus c. So looks like I have my a is 5, my b is a negative 17, and my c is a plus 32. And x squared is my biggest power here, so this one, yes, is quadratic. 3x minus 5. So we don't have an x squared here, and there is a caveat here that a cannot be 0. Okay? B can be 0 or c can be 0, but a cannot be 0. And since we don't have an x squared term here, and in fact this is linear, hopefully you recognize that from the last chapter, this is not quadratic. And then we have one more. So this one actually appears to be in factored form. And if that's the case, I would have a times x minus r, x minus s. So it looks like maybe my a is a 1, my r is a 2, and my s is a negative 4. So that does fit this pattern here. Another way of approaching this would be to FOIL this out. So I get x squared minus 2x plus 4x minus 8. So x squared plus 2x minus 8, and that does fit this form here, and I have that x squared term, and it's my biggest power. So yes, this one is also quadratic.